Hello, my dear sleepy friends, and welcome back to Hafee Sleep. Wherever you are in the world, whatever time it is for you right now, whether you're winding down for the night, starting your morning, or simply finding a quiet moment in between, we are so glad you're here to relax with us. Tonight, we're going on a very special journey, a starlit voyage to the very edge of our solar system, to solve a cosmic mystery that once confused the entire world. Have you ever wondered? Why did Pluto get demoted? Why is it no longer considered a planet? The story is so much more than a simple change in a textbook. It's a tale of discovery, of scientific debate, and ultimately, a revelation that unlocked a hidden kingdom of frozen worlds. So get comfortable, close your eyes, and let your mind drift among the stars. We're about to uncover the fascinating truth about our most famous cosmic underdog, Pluto. And while you're relaxing with us, if this journey sparks your curiosity, we'd be so grateful if you could help our community grow. Hitting that subscribe button and giving the video a like helps us bring more peaceful explorations to you. Most importantly, we'd love to hear from you. The world of Hafee Sleep is a global one. So, as you settle in, please comment below and tell us where you're watching from and what time it is there. It's always wonderful to see our community of curious minds connecting from all corners of the globe. All right, let's begin our journey. Imagine, if you will, a model of our solar system. Not the full, complex one with its asteroids and comets, but the classic one, the one you probably built out of styrofoam balls in school. There's the bright yellow sun at the center, a fiery marble of light. Then, orbiting it, a neat line of painted spheres, Mercury, a tiny baked speck, Venus, shrouded in white, our own beautiful blue and green Earth, rusty red Mars, the great striped king, Jupiter, Saturn with its magnificent rings, Uranus, a serene blue-green, Neptune, a deeper, colder blue, and out there, on the very edge, a lonely little speck of rock and ice called Pluto. For generations, this 9-planet lineup was a fundamental fact of life, a cosmic truth as certain as the sky being blue. It was the order of things. It was tidy. But science, my friends, is rarely tidy. It is a living, breathing process of discovery, a conversation with the universe that is constantly evolving. And in 2006, that conversation took a dramatic turn that shocked the world, confused schoolchildren, and broke the hearts of space enthusiasts everywhere. The announcement came down like a galactic decree. Pluto, the 9th planet, the underdog of our solar system, was being fired, demoted, stripped of its planetary status. Now, if you're like most people, your first reaction was probably a sense of betrayal. What did Pluto ever do to them? You might have thought. It was just minding its own business out there in the dark. It felt like a personal affront, a rewriting of a cherished childhood memory. But here's the secret, the real story that's far more fascinating than a simple demotion. Pluto didn't change. We did. Our understanding of the solar system grew up. We looked closer, we saw more, and we realized that the universe is far stranger, far more complex, and far more wonderful than we ever imagined from our little styrofoam model. So, let's embark on a journey to the frozen frontier of our solar system to understand not just what happened to Pluto, but why. This isn't a story of a planet being cast out. This is a detective story, a tale of cosmic discovery that forced us to ask the most fundamental of questions. What exactly is a planet? And by the time we're done, you'll see that Pluto's story isn't a tragedy. It's the key that unlocked a hidden kingdom of worlds we never knew existed, a kingdom where Pluto is not a castaway, but a king. Our story really begins not in 2006, but decades earlier, in the mind of a man named Clyde Tombaugh. Astronomers had long predicted a planet X out beyond Neptune, its presence hinted at by tiny, unexplained tugs on the orbits of Uranus and Neptune. Now, to truly appreciate the weight of that moment, that tiny speck shifting in a sea of static stars, we have to put ourselves in Clyde Tombaugh's shoes, and indeed, in the world of 1930. It's almost impossible to overstate how different the technological landscape was. This was an era before digital cameras, before computers, before even the widespread use of calculators. Astronomy was a discipline of immense patience, of physical endurance, and of literally photographic memory. The night sky was captured on glass plates coated with a sensitive emulsion, a chemical layer that reacted to light. These plates were the hard drives of their day, fragile and heavy, each one a unique snapshot of a specific patch of cosmos at a specific moment in time. The search for Planet X wasn't some wild fringe idea. It was a serious scientific pursuit, born from the very bedrock of physics, Newton's laws of motion and gravity. Astronomers had these laws that beautifully described the orbits of the planets. You could plug in the mass of the sun, the mass of a planet, and its distance, and mathematically predict its path with incredible accuracy. But for the two outermost known planets, Uranus and Neptune, there was a tiny, nagging discrepancy. Their actual observed positions in the sky didn't quite match the positions predicted by the math. It was as if something, some unseen gravitational hand, was giving them a very slight, almost imperceptible tug. The most logical explanation was that another mass, another planet, was out there beyond Neptune, its gravity perturbing their orbits. This hypothetical world was dubbed Planet X, the X standing for the unknown, a mystery waiting to be solved. The man who became most obsessed with this mystery was Percival Lowell, a wealthy Bostonian with a passion for astronomy. He's a fascinating character in his own right. Today, he's perhaps best known for his fervent and ultimately incorrect belief in canals on Mars, which he thought were evidence of a great civilization. But his legacy is far more mixed and interesting than that. He used his fortune to establish the Lowell Observatory in Flagstaff, Arizona, specifically chosen for its high altitude and clear, dark skies. And he dedicated the later years of his life and a significant portion of his wealth to the search for Planet X. He performed complex calculations to predict where it might be, and began the painstaking photographic search. But the technology of his time, and perhaps the sheer difficulty of the task, meant he died in 1916 without having found it. The search was abandoned for a number of years, a seemingly unfulfilled dream. But the dream didn't die. In 1929, the observatory, under new direction, decided to revive the search. They needed a fresh pair of eyes, someone with immense patience and a sharp visual acuity. They didn't hire a famous established astronomer. Instead, they offered the job to a 23-year-old farm boy from Kansas named Clyde Tombaugh. Tombaugh was a self-taught astronomer. He had built his own telescopes from scratch, grinding the mirrors himself using parts from his family's farm machinery. He had made detailed drawings of the planets Jupiter and Mars, and he had sent them to the Lowell Observatory, not applying for a job, but just seeking expert opinion. The quality of his work was so impressive that when they needed someone for the grueling Planet X search, they thought of him. It's a wonderful bit of history, the ultimate cosmic detective job being handed to a bright, passionate amateur. He was hired as an assistant, and arrived in Flagstaff with his telescopes in a crate, full of hope and determination. And grueling is the only word for the task he faced. The telescope he would use was a 13-inch astrograph, a sophisticated instrument designed specifically for photography. Every clear night, he would take a photograph of a specific predetermined section of the sky. But you couldn't just look at one plate and see a planet. The magic, the entire crux of the method, was in the comparison. He would take a photograph of the same star field a few nights later. Then came the central tool of the investigation, the blink comparator. Let's picture this device, because it's absolutely crucial to the story. Imagine a large, microscope-like machine. It had two eyepieces, side by side, and a mechanism that allowed the user to rapidly switch the view from one glass plate to the other. The plates were positioned so that the star fields aligned perfectly. Now, when you looked through it, you'd see a vast, dense carpet of stars. When you pressed a lever to blink between the two plates, taken nights apart, the vast majority of the stars, being effectively infinitely far away, would not move. They would stay perfectly fixed. But any object that was much, much closer within our own solar system would have moved in its orbit around the sun in the interval between the two exposures. So, against a background of static stars, this object would appear to jump back and forth. It was a way to make motion visible. The area of the sky he had to search was enormous, vast sweeps along the ecliptic, the plane in which the planets orbit. Each photographic plate covered just a tiny fraction of this area, and each plate contained not dozens, not hundreds, but hundreds of thousands of stars. Tombaugh's job was to systematically blink every single one of these pairs of plates, square inch by square inch, staring into this dizzying array of dots, searching for the one dot that didn't behave like the others. He later described it as the most tedious work he could imagine. It was like searching for a single specific grain of sand on a vast beach, and the only clue was that this one particular grain might have shifted its position by a millimeter. The strain on the eyes, the neck, the back must have been immense. He worked through the winter of 1929-1930, month after month with no success. It would have been easy to get discouraged, to think that perhaps his illustrious predecessor, Percival Lowell, had simply been wrong. But then, on February 18, 1930, everything changed. Tombaugh was examining a pair of plates taken on January 23rd and January 29th. He was methodically working his way through the plates, a region in the constellation of Gemini. And then he saw it. In the vast static sea of stars, one faint 15th magnitude speck jumped. It was a tiny, almost insignificant-looking dot, but it moved. His heart must have raced. He had to be sure. He checked a third plate, taken on January 21st, and there it was again, in the predicted position. This was no asteroid. Its slow motion indicated it was very far away. This was it. This was the ghost. This was Planet X. The caution and protocol that followed are a testament to scientific rigor. He didn't run out into the street shouting. He quietly told the observatory director, Vesto Slifer, who then gathered the other senior astronomers. They spent weeks confirming the discovery, taking more photographs to refine the orbit, making absolutely certain before they told the world. The announcement was made on March 13th, 1930, which would have been Percival Lowell's 75th birthday. It was a deliberate and poignant tribute. The news, as you can imagine, was a global sensation. In the depths of the Great Depression, a time of immense hardship and worry, The discovery of a new planet captured the public's imagination like nothing else. It was a story of exploration and triumph, a reminder that there were still new frontiers to be conquered, even if they were millions of miles away. It was the first planet discovered by an American, which added a layer of national pride for a country in need of some good news. Then came the question of a name. The Lowell Observatory, having made the discovery, had the right to name it, and they were flooded with suggestions from all over the world. Names from mythology were the tradition, and many were proposed: Cronus, Minerva, Zeus. But the name that ultimately stuck came from a most unexpected source: an 11-year-old girl named Venetia Burney, who was having breakfast with her grandfather in Oxford, England. Her grandfather was reading aloud the thrilling news from the newspaper about the discovery of a new planet. And Venetia, who was fascinated by classical mythology, suggested the name Pluto for the Roman god of the underworld. It seemed fitting for a world that dwelled in such perpetual, sunless gloom at the edge of the known solar system. Her grandfather was so taken with the idea that he mentioned it to a friend who was a professor of astronomy at Oxford, who then telegrammed the suggestion to the Lowell Observatory. The astronomers at Lowell loved it for several reasons. Firstly, the mythological connection was perfect. But there was a beautiful secondary reason. The first two letters, P and L, were the initials of Percival Lowell. It was a way to immortalize the man whose vision had set the whole search in motion. It was a name that honored both the ancient myths and the modern quest for knowledge. The name was officially adopted, and a wonderful postscript to the story is that Venetia Burney, later Venetia Fair, lived long enough to see the New Horizons spacecraft launched toward Pluto in 2006. She said she was quite pleased that her childhood suggestion had traveled so far, both in acceptance and in literal distance. So, Pluto was born into our collective consciousness with a sense of romance, triumph, and poetry. It was the little planet that could, discovered by a persevering farm boy and named by a clever schoolgirl. For 76 years, that's how we knew it, as the ninth planet, a small, mysterious world on the fringe of everything. But even at the moment of its discovery, there were tiny clues, subtle hints that Pluto was an oddity. The first was its size. Early estimates were rough. Initially, based on its faintness and assumed reflectivity, it was thought to be roughly Earth-sized. But as decades passed and observations improved, particularly with the advent of more powerful telescopes, those estimates kept shrinking. It became clear that Pluto was not a giant. It was, in fact, shockingly small. By the 1970s, we knew it was smaller than Mercury, smaller than Mars, and even smaller than our own moon. This was puzzling. The gravitational perturbations that had hinted at Planet X suggested a much more massive object. We now know that those perturbations were largely observational errors. Neptune's mass had been slightly miscalculated. Once the math was corrected, the need for a large Planet X mostly vanished. But by then, Pluto was already firmly entrenched in the planetary lineup. It was a planet by accident, a world discovered serendipitously while searching for a phantom that didn't really exist. Its small size was the first crack in the facade, a quiet suggestion that maybe, just maybe, Pluto was a different kind of beast altogether, living in a part of the solar system we were only just beginning to imagine. For decades, that's where things stood. 9 planets. End of story. Textbooks were printed, models were built, and we moved on to other discoveries. But astronomers, being the curious folk they are, never really stopped looking. And as telescopes got bigger and better, particularly with the advent of powerful instruments like the Hubble Space Telescope, our view of the outer solar system started to get crowded. For a long time, the Kuiper Belt was just a theory. You see, to really grasp why the discovery of the Kuiper Belt was such a monumental shift in thinking, we have to completely reimagine the mental map we all have of our solar system. That classic image, the one with the 9 or now 8 planets orbiting the sun like runners on neat circular tracks, is not so much wrong as it is incomplete. It's like looking at a map of a country that only shows the capital cities and the major highways connecting them. It tells you where the big important places are, but it gives you no sense of the sprawling countryside, the small towns, the forests, the rivers, or the vast untouched wildernesses that lie in between and beyond. Our solar system isn't just a collection of 8 large worlds. It's a bustling, dynamic metropolis filled with all sorts of inhabitants, from colossal giants to tiny pebbles, and Pluto's story is the story of us finally discovering the sprawling hidden suburbs of this cosmic city. So let's build this new map together from the ground up. Let's start downtown, in the heart of the action. The inner solar system, from the sun out to the orbit of Mars, is the urban core. It's dense, rocky, and relatively warm, bathed in the sun's intense light. Here, we find the terrestrial planets, Mercury, Venus, Earth, and Mars. They're like the great, historic city centers, built from the heavy metallic and rocky materials that could withstand the heat close to the young, furious sun. They orbit the sun quickly. Their years are short, because they're on a tight, fast-paced commute around the central star. The space between them, while vast to us, is relatively small on a solar system scale. It's a region bustling with activity, not just from the planets, but from asteroids, which are like the commuter trains and delivery trucks zipping between the boroughs. Just beyond Mars, we hit the first major ring road, the asteroid belt. Now, popular culture often depicts this as an impossibly dense field of tumbling rocks, a navigational nightmare for any passing spacecraft, like trying to drive through a chaotic demolition derby. But in reality, it's much more like a vast, sprawling suburban industrial estate. The individual asteroids are incredibly spread out. If you were standing on one asteroid, the chances of seeing another with your naked eye would be almost zero. It's not a crowded obstacle course. It's a zone of scattered debris, the leftover building materials from the solar system's construction that never managed to clump together into a proper planet, largely thanks to the immense gravitational influence of the bully next door, Jupiter. So, the asteroid belt is our solar system's first wilderness, but a relatively tame one, a reminder of the construction that never quite finished. Now, we move beyond the belt, and the character of the solar system changes dramatically. We enter the realm of the gas giants, Jupiter, Saturn, Uranus, and Neptune. These are not like the dense, rocky downtown planets. These are the sprawling, majestic estates on the outskirts of the city. They are colossal, made mostly of hydrogen and helium, with possibly small rocky cores deep inside. They are the gravitational aristocrats of our system, massive enough to have captured entire entourages of moons, some of which, like Jupiter's Ganymede or Saturn's Titan, are themselves larger than the planet Mercury and are worlds of stunning complexity in their own right. These gas giants also boast magnificent rings, with Saturn's being the most famous, delicate necklaces of ice and rock that circle the planets. Their orbits are much wider and slower. A year on Jupiter is 12 Earth years. On Neptune, it's a breathtaking 165 Earth years. Life out here is slower, grander, and governed by the immense gravitational pull of these giants. For a very long time, we thought Neptune marked the edge of the city. Beyond it, we imagined, was just empty space, a dark, silent highway leading to the next star system, light years away. Pluto, discovered out there orbiting in the gloom, was a puzzle. It was small and rocky like a downtown planet, but it lived way out in the exurbs, far beyond the gas giants. It was like finding a single, solitary, quaint little cottage sitting all by itself in the middle of what we thought was an empty desert. It didn't make a lot of sense. Why was it there? Was it a planet that had been flung out from the inner solar system? Was it a lone stranger? For decades, it was our cosmic mystery, the oddball at the edge of town. But a few sharp-minded astronomers had a different idea. They thought, what if it's not alone? What if that desert isn't empty at all? What if it's actually a vast frozen forest, and Pluto is just the first tree we happen to see? This was the brilliant hypothesis put forward by astronomers like Gerard Kuiper and Kenneth Edgeworth. Their reasoning was based on how we think the solar system formed. About 4.6 billion years ago, a giant cloud of gas and dust collapsed to form the Sun. The leftover materials spun around the infant star in a flat disk like a spinning pizza dough. Closer to the Sun, where it was hot, only metals and rocks could solidify, leading to the terrestrial planets. Further out, it was cool enough for ices to form, not just water ice, but frozen methane, ammonia, and carbon dioxide. These ices acted like glue, allowing the gas giants to rapidly accumulate immense size. But the theorists proposed that beyond Neptune, the disk of material was too spread out for a large planet to form quickly. Instead, countless small bodies of ice and rock coalesced. This would be a vast reservoir of primordial material, a deep freeze archive holding clues to the very beginning of the solar system. Gerard Kuiper, in particular, suggested that a disk of such objects might exist just beyond Neptune. For decades, however, this Kuiper belt, as it became known, was just a theory. The objects it predicted were too faint, too small, and too far away for any telescope on Earth to see. It was a compelling idea, but without proof, it remained a ghost. A possible explanation for Pluto's lonely existence, but nothing more. The turning point came with technology, specifically the development of massive sensitive electronic light detectors called charge-coupled devices, or CCDs. These are the same technology that powers the digital camera in your phone, but on a much, much larger and more sensitive scale. They revolutionized astronomy. Compared to the old photographic plates that Clyde Tombaugh painstakingly used, CCDs are incredibly efficient at capturing light. They can detect incredibly faint objects, and they feed the data directly into computers. This meant astronomers could now systematically scan the skies for these faint, slow-moving dots in a way that was impossible before. And so, in the 1990s, the hunt began. Astronomers started pointing these powerful new electronic eyes towards the regions beyond Neptune, and almost immediately, they started finding things. The first Kuiper belt object, other than Pluto, was discovered in 1992 by astronomers David Jewett and Jane Liu. It was a small, faint world, designated 1992 QB1. It was a moment of profound vindication. The forest existed. The theoretical ghost had taken solid form, and then the floodgates opened. Once astronomers knew what to look for and how to look for it, the discoveries came thick and fast. Dozens, then hundreds of Kuiper belt objects were cataloged. The empty desert beyond Neptune was suddenly teeming with life. A vast swarm of icy bodies, each orbiting the sun in a frozen, slow-motion dance. We realized that Pluto was not a solitary cottage in a desert. It was one house in a massive, previously hidden suburban sprawl that stretched billions of miles into space. The Kuiper Belt wasn't just a small ring. It was a gigantic donut-shaped region, much wider than the inner solar system, containing perhaps hundreds of thousands of objects larger than 60 miles across and countless millions of smaller ones. This was the first major blow to Pluto's unique status. It was no longer a singular oddity. It had a context. It was part of a population. But the real crisis, the event that would force a cosmic reckoning, was still to come. As astronomers cataloged more and more of these KBOs, they began to find some that were substantial. They weren't all tiny snowballs. They found worlds like Quaoar, Makemake, and Haumea, some of which were half the size of Pluto or more. The solar system's third zone was not just a field of rubble. It contained a whole spectrum of worlds, some of them significant in size. And then, in 2005, a team led by Mike Brown at the California Institute of Technology made the discovery that would change everything. Using the powerful 48-inch Samuel Oschin telescope at Palomar Observatory, they found an object that was not just another KBO. Initial measurements suggested it was not only larger than Pluto, but it also had its own moon, which allowed them to calculate its mass. It was a substantial world. They had, in essence, found a twin to Pluto, but a twin that was potentially bigger and more massive. They initially nicknamed it Xena, after the television warrior princess, but its official designation became Eris, named after the Greek goddess of discord and strife. The name could not have been more appropriate. Eris's discovery threw the astronomical world into complete turmoil. It was the catalyst for the entire crisis. The unspoken question that had been hanging in the air since the discovery of the Kuiper Belt now demanded an answer. What is a planet? If Pluto, with its small size and its location in the crowded Kuiper Belt, was considered a planet, then surely Eris, which was bigger and also in the Kuiper Belt, must be a planet too. And if Eris was a planet, then what about the other large KBOs like Makemake and Haumea? Were they planets? Where would we draw the line? Would we soon have 10, 20, or even 50 planets? The very word planet, which means wanderer in Greek, was in danger of losing its meaning. It would become a category so broad as to be useless for scientific classification. This was the dilemma that landed squarely on the desks of the International Astronomical Union, IAU, the body responsible for naming and classifying celestial objects. They were facing a fundamental taxonomic problem, much like biologists who have to decide what distinguishes a species or a family. The comfortable, simple solar system of our childhood was gone, replaced by a complex, messy, and far more interesting reality. The discovery of Eris was the pebble that started the avalanche, forcing a group of the world's leading astronomers to sit down in a room and try to define a word that everyone thought they already understood. The stage was set for the great planetary debate of 2006, a debate that would end with Pluto's demotion, but would open up our understanding of the solar system to a breathtaking new scale. The Kuiper Belt was no longer a theory. It was a frontier, and Pluto was its most famous citizen, waiting for its fate to be decided. So, there they were, the astronomers of the International Astronomical Union, gathered in Prague in the summer of 2006. You have to picture the scene. This isn't a room of cold, unfeeling scientists arbitrarily deciding to pick on Pluto. These are people who, for the most part, grew up with the 9-planet model too. Many of them had posters of the solar system on their walls as kids. They feel the same affection for that little world as anyone else. But they are facing a professional crisis. The discovery of Eris has forced their hand. They can no longer rely on tradition or sentiment. They need a definition, a scientific definition, a rule that can be applied consistently across the cosmos. And this is much, much harder than it sounds. Imagine you're asked to define a simple, everyday word like chair. You might say, it's something you sit on. But is a stool a chair? Is a bench a chair? Is a tree stump you sit on a chair? The moment you try to pin down a definition, you find exceptions and edge cases. Now, magnify that problem to a cosmic scale. They are trying to define a planet, a category of object that exists in the vast, messy, and unpredictable laboratory of nature. The debate in Prague was passionate, sometimes heated. There were multiple proposals on the table, and the fate of Pluto hung in the balance. One early proposal actually would have saved Pluto's planethood and added several new planets at the same time. It focused mainly on the roundness criterion. The idea was simple. If it's big enough to be pulled into a sphere by its own gravity, it's a planet. This would have included not just Pluto and Eris, but also the large asteroid Ceres, and even Pluto's own large moon, Charon, because they orbit a common center of gravity, a point called a barycenter that lies outside of Pluto. This would have given us at least 12 planets overnight, with the potential for dozens more as we discovered other round objects in the Kuiper belt. For a moment, it seemed like this might be the solution, a big, inclusive solar system. But many astronomers argued that this definition was too broad. It focused only on the intrinsic properties of the object itself, its shape, and ignored its relationship to its cosmic environment. This, they felt, was a critical missing piece. After all, the root of the entire problem was that we had found a whole population of round objects in the Kuiper belt. Classifying them all as planets would make the term less meaningful from a dynamical perspective, that is, from the perspective of how bodies interact and govern their orbital space. It would be like a zoologist declaring that every four-legged animal is a dog. It might be technically true based on one characteristic, but it ignores the profound differences between, say, a dog, a cat, a cow, and a lizard. A cow is a magnificent animal, but calling it a dog doesn't help us understand its nature or its place in the ecosystem. So, after much back and forth, the final definition emerged. It contained 3 clauses, 3 hurdles that an object must clear to be called a planet. Let's not just read them. Let's live inside them, understand the thinking behind each one, and see why they were chosen. The first one seems so obvious it's almost comical. A planet must be in orbit around the sun. Well, of course, this is the basic requirement that sets the stage. It immediately rules out moons. Titan, Jupiter's Ganymede, and our own moon are all spectacular, complex worlds, some with atmospheres and even subsurface oceans. But they are not planets because their primary gravitational allegiance is to their host planet, not directly to the sun. They are satellites. This first rule draws that fundamental line in the sand. Pluto, however, orbits the sun directly. So first hurdle cleared. No problem. The second criterion is where we get into the real physics, and it's a beautiful piece of natural law. The official wording is a bit of a tongue twister. It must have sufficient mass for its self-gravity to overcome rigid body forces so that it assumes a hydrostatic equilibrium, nearly round shape. Let's unpack that like we're opening a carefully wrapped gift. Rigid body forces is just a fancy way of saying the strength of the material itself. Think of a lump of clay. If it's small, you can mold it into any shape, a cube, a long snake, a star, and it will hold that shape. The clay's own internal stickiness and strength are enough to resist gravity. This is what happens with small asteroids and comets. They are like cosmic potatoes, lumpy and irregular, because the chemical bonds holding their rock and ice together are stronger than their own minuscule gravity. But now, imagine you keep adding more and more clay to your sculpture. As it gets bigger and heavier, the weight at the bottom starts to press down. The peaks and valleys you sculpted begin to sag. If you could make it massive enough, the entire thing would eventually collapse under its own weight, smoothing out into the most efficient shape possible, a sphere. This is hydrostatic equilibrium. It's the point where gravity, the great leveler, wins. The material, whether it's rock, ice, or gas, behaves like a fluid over geological timescales, settling into a ball. This is a fundamental transition in the life of a celestial body. When an object becomes round, it signifies that it has enough mass for gravity to trigger internal geological processes. It can differentiate, meaning heavy elements like iron sink to the core, while lighter rocks rise to the surface, creating layers. This can lead to volcanism, tectonics, and the generation of magnetic fields. Roundness isn't just about looks. It's a sign of a geologically active world. Pluto, as we would later see in stunning detail from the New Horizons mission, is unquestionably round and fantastically geologically active. It has mountains, glaciers, and a complex layered structure. So, second hurdle, cleared with flying colors. Pluto is, without a doubt, a complex and interesting world. But then we come to the third criterion, the deal breaker, the one that has caused all the fuss. It must have cleared the neighborhood around its orbit. This is the trickiest one to grasp because it's not about what the object is, but about what it has done. It's a historical test. It asks, over the billions of years since the solar system formed, has this object become the gravitational master of its orbital domain? Let's be perfectly clear what cleared does not mean. It does not mean the orbit has to be pristine and empty. If that were the case, then no planet would qualify, not even Jupiter. Earth's orbit is crossed by thousands of asteroids known as near-Earth objects. Jupiter's orbit is shared with two huge swarms of asteroids called the Trojans, which orbit ahead of and behind the gas giant. So what does it mean? It means that the planet must be the overwhelmingly dominant gravitational force in its orbital zone. Its mass must be so much greater than the combined mass of everything else that shares a similar orbital path that it is either absorbed, ejected, or gravitationally dominated all other significant competitors. It is the king of its celestial hill. Think of it like this. Imagine Earth's orbit around the sun is a vast circular running track. Earth is a massive professional athlete running in the inside lane. Now, on that same track, there are also some pebbles, a few small gravel stones, and maybe even a couple of larger rocks. These are the asteroids that cross our path. But compared to the athlete, their mass is insignificant. The athlete doesn't even notice them. If one ever gets in the way, the athlete's gravity will either pull it in, it gets absorbed, or give it a gravitational kick that sends it off the track entirely. Earth is the boss of that lane. It has cleared its neighborhood by being the dominant presence. Now let's travel out to Pluto's neighborhood. Pluto's orbit isn't a lonely track. It's a bustling, icy freeway interchange in the heart of the Kuiper Belt. Pluto is not a massive athlete. It's more like a regular-sized car, a very interesting car, with a fancy paint job and a great sound system, sure. But it's surrounded by thousands of other cars, trucks, and vans of all sizes, all traveling along the same stretch of orbital highway. Some of these other vehicles, like Eris, are just as big as Pluto, or bigger. Pluto is not the boss here. It doesn't control the traffic. It's just one commuter among many. It has not cleared its neighborhood. It lives in a densely populated part of the cosmic city. The numbers make this stark. Astronomers calculate something called the planetary discriminant, U, which is the ratio of the planet's mass to the total mass of all other objects that share its orbital zone. For the 8 planets, this number is enormous. Jupiter's U is over 50,000. Earth's is a whopping 1.7 million. This means Earth is 1.7 million times more massive than everything else in its orbital neighborhood combined. It is the undisputed gravitational master. And Pluto's planetary discriminant is less than 1. Its mass is only about 0.07 times the total mass of the known Kuiper Belt objects. In other words, the other objects in its zone are together more massive than Pluto itself. It is not the king of the Kuiper Belt, it is a member of the parliament. A notable member, to be sure, but not the ruler. This third criterion is what fundamentally separates the 8 planets from all the other round bodies in the solar system. It recognizes that a planet isn't just defined by its own characteristics, but by its dynamical relationship with its surroundings. The 8 planets are the gravitational giants that have sculpted the architecture of our solar system. They are the ones that, through their immense gravity, have carved out clear zones of dominance for themselves. And so, the IAU had to make a choice. By this strict 3-part definition, Pluto did not qualify. It was a round object orbiting the Sun, but it had not cleared its orbit. To acknowledge this new understanding, they created a new category, the dwarf planet. This was not meant as an insult. It was a precise scientific classification for objects that are large enough to be round and orbit the Sun, but which live in populated areas like the asteroid belt, Ceres, or the Kuiper Belt, Pluto, Eris, Makemake, Haumea, and others. The vote was taken on August 24, 2006. It was not unanimous. Of the astronomers who remained for the vote, many had already left the conference. A majority voted in favor. And just like that, with the bang of a gavel, the solar system we knew was changed forever. The public reaction, as we know, was a mix of confusion, disappointment, and even outrage. It felt like a demotion, but from a scientific perspective, it was a necessary act of classification. It was about placing Pluto with its true family. Pluto is not a misfit planet. It is the prototype of a whole new class of worlds, the most famous denizen of the vast and mysterious Kuiper Belt. The decision wasn't about kicking Pluto out. It was about finally understanding where it truly belongs. Think of it this way. Let's say you're a biologist trying to classify animals. You have a category for big cats. Lions, tigers, leopards. They share certain traits. Now you find a house cat. It's clearly related to the big cats. It's furry, it has whiskers, it meows, sort of. But is it a big cat? No. It belongs to a different category because its size, ecology, and behavior are fundamentally different. That doesn't make the house cat any less fascinating. It just helps us understand the relationships between different animals. Pluto is the solar system's house cat. It's a fascinating, complex world, but it's part of a different population than the gravitational giants we call planets. The demotion of Pluto, while emotionally difficult, was a sign of scientific progress. It meant our map of the solar system was becoming more accurate, more detailed. We were no longer just seeing the major landmarks. We were starting to understand the entire geography. And the best part of this story, the part that truly vindicates Pluto's importance, came 9 years after its demotion. Now, the story of Pluto's reclassification could have ended in that conference room in Prague in 2006. It could have been a dry academic footnote, a change in a textbook that left a lingering sense of loss. But the universe, in its wonderful way, had already set in motion an event that would transform this story from one of debate into one of pure, unadulterated wonder. Because hurtling through the silent blackness of space, already 3 years into its epic journey, was a little robotic ambassador named New Horizons. Its launch in January 2006 and the IAU's vote in August of that same year created one of the most delicious ironies in the history of exploration. A spacecraft was sent to explore a planet and arrived 9 years later to find it was now a dwarf planet. But far from undermining the mission, this timing made it all the more profound. To appreciate what New Horizons accomplished, we need to understand the sheer scale of the challenge. This wasn't like going to Mars, a trip of a few 100 million miles that takes 6 to 9 months. This was a voyage to the edge of the known solar system, 3 billion miles. Think about that number for a second. It's so large it becomes abstract. If you were to drive a car at a steady 60 miles per hour, non-stop, day and night, it would take you over 5,700 years to travel that distance. New Horizons, one of the fastest spacecraft ever launched, riding a powerful Atlas V rocket and getting a gravitational slingshot boost from Jupiter, still took 9.5 years. For most of that time, it was just a speck of light to its controllers on Earth, silent for long periods in a state of electronic hibernation to conserve power, only waking up periodically to report that all was well. It was the ultimate test of patience and long-term planning. And as it finally approached its target in early 2015, the anticipation was electric. For months, the images streaming back got better and better. Pluto transformed from a blurry dot into a tiny disk, and then finally, into a world. The scientists on the mission would release new images each week, each one sharper than the last, and the world watched alongside them, sharing in the collective awe. But nothing could have prepared anyone for the first high-resolution images taken during the flyby on July 14th, 2015. Because the Pluto that was revealed was not the dead, boring ice ball that many had predicted. The first thing that struck everyone was the heart. A vast, bright heart-shaped region dominating one hemisphere, instantly visible even from a distance. It was so perfect, so symbolic, that it seemed almost too good to be true. They named it Tombaugh Regio, in honor of Clyde Tombaugh, the man who had painstakingly searched for that tiny moving speck 85 years earlier. It was a beautiful and fitting tribute. But what was it? As the data poured in, we learned that this heart is a colossal glacier, but not of water ice. This is a glacier of solid nitrogen, carbon monoxide, and methane. On Earth, we have water ice. On Pluto, with surface temperatures hovering around 380 degrees Fahrenheit, these gases freeze solid and behave like geological materials. This heart is a vast, slowly convecting plain of exotic ice, with cells of frozen nitrogen rising and falling like a giant slow-motion lava lamp, smoothing out the surface and creating those incredible polygonal patterns we see. But the surprises didn't stop there. Right next to this smooth, youthful heart, on its western edge, stood a range of mountains. But these weren't just any mountains. they jutting up to heights of 11,000 feet, rivaling the Rocky Mountains on Earth. And here's the incredible part. They are made of water ice. Now, on Earth, water ice is relatively soft. You can't build a mountain out of it. But at Pluto's temperatures, water ice is as hard as rock. It forms a bedrock upon which the geology of this strange world is built. And these mountains showed very few impact craters, meaning they are geologically young. This was the bombshell. A small, cold world, so far from the sun, should have been geologically dead for billions of years. Its internal heat from formation should have long since leaked away. Yet here was evidence of recent, perhaps even ongoing geological activity. Pluto was not a fossil. It was alive. Then there was the atmosphere. New Horizons looked back at Pluto after it had flown past, capturing an image of the dwarf planet backlit by the sun. And it revealed a thin, hazy, and stunningly blue atmosphere. Multiple layers of haze extended high above the surface, created when methane is broken apart by the sun's weak light, and forms more complex hydrocarbon molecules, which eventually snow down onto the surface, giving it a reddish tint. This was an active, dynamic system, a world with weather and seasons. Albeit on a time scale and with chemistry, we are only beginning to understand. The message from New Horizons was clear and powerful. The IAU's decision had not diminished Pluto in the slightest. In fact, the mission demonstrated that the category of dwarf planet was filled with worlds of staggering complexity and beauty. The label didn't matter. The reality was what took our breath away. Pluto was every bit as fascinating as Mars or Mercury. It taught us that geological activity isn't just a function of size or proximity to the sun. Pluto likely has a subsurface ocean of liquid water, kept from freezing by the heat generated from the decay of radioactive elements in its core, and this internal heat might be driving the activity we see on the surface. It forced us to completely rewrite the textbooks on planetary science. But the adventure wasn't over. New Horizons, healthy and with fuel to spare, was given a new mission: to visit another object deep in the Kuiper Belt. After a frantic search using the most powerful telescopes on Earth and even the Hubble Space Telescope, scientists found a target that New Horizons could reach with its remaining fuel. They named it Arakoth, a Powhatan word meaning sky, chosen to honor the indigenous peoples of the Chesapeake Bay region. On January 1st, 2019, New Horizons performed the most distant flyby in history, whistling past this tiny, mysterious world over 4 billion miles from Earth. And what it found was like a time capsule. Arakoth is not round. It looks like two lumpy pancakes gently stuck together. It is what scientists call a contact binary, two separate objects that formed separately and then gently, slowly merged together in the very early days of the solar system. Its surface is smooth and remarkably uncratered, suggesting it has been preserved in the deep freeze of the Kuiper Belt for over 4 billion years. Studying Arakoth is like looking at a fossil from the dawn of planetary formation. It provides crucial evidence for how the very building blocks of planets, called planetesimals, first came together. It suggests that the process was a gentle one, with objects slowly coalescing from the dust of the primordial disk, rather than through violent, high-speed collisions. This second act of the New Horizons mission underscored the true importance of the Kuiper Belt. It's not just a collection of interesting worlds. It's a cosmic archive. It's the solar system's attic, where the original building materials and blueprints have been kept perfectly preserved. By studying Pluto and Arakoth, we are reading the story of how our entire planetary system, including Earth, was built. So, where does that leave us today? Pluto is not a planet. mysterious members of the Kuiper Belt, a whole new class of solar system objects that we are only beginning to explore. Its demotion wasn't a punishment, it was a promotion. It went from being the smallest, weirdest planet to being the prototype, the king of an entire new kingdom of worlds. The story of Pluto is the story of science itself. It's a story of how we learn and grow. We start with simple models, with 9 styrofoam balls on a wire. Then we look closer. We discover new things that don't fit the old model. We are forced to question our assumptions, to refine our definitions, to create a new understanding that is richer, more complex, and more truthful than the one we had before. It can be uncomfortable. It can feel like losing something familiar. But what we gain is so much greater, a deeper, more wondrous view of our place in the cosmos. Pluto taught us that the solar system is bigger and wilder than we ever dreamed. It's not a neat and tidy backyard with 8 large plants and a little one at the end. It's a vast, sprawling system with a vibrant inner city, gaseous suburbs, and an immense, unexplored wilderness teeming with icy worlds, each with its own story to tell. Pluto will always hold a special place in our hearts as the first of these frontier worlds we ever laid eyes on. It's not the 9th planet. It's the gateway to the 3rd zone of the solar system. And that is a far more exciting title to hold. So the next time you look up at the night sky, think of Pluto, not with sadness for its demotion, but with awe for what it represents. Our endless, curious, and ever-evolving quest to understand the universe. It's still out there, orbiting in the deep freeze, a testament to the fact that discovery is never over. The universe always has more secrets to reveal. Good night. Have a deep, calm sleep.